Fine. So in today's class, let's talk about a new topic, which is tactics. Now, these tactics are, you can say, ways to achieve quality. Right? These are some of the ways to achieve quality. So what we had previously was from architecture, we had design below it, and now further we are going for tactics. So several tactics will be there in a particular design. Right, architectural design right now we are addressing. So what we are trying to do is with the help of tactics, first thing is that it's a way to achieve quality, and secondly we are also trying to control the quality. So what we can say is that these tactics are design options for the architect in order to achieve quality. So what we do in this particular thing is we provide the stimulus, and we use tactics to control the response based on various qualities, and then as an output we are getting some response. Now let's add some more points to this particular thing, which is tactic. So from this diagram you might have got an idea that this is an action which is carefully planned to achieve a specific end. And as I said earlier, these patterns package the tactics. That means multiple tactics are packaged in a simple single design. So your architectural tactic is in some or the other way a means of satisfying a quality attribute through the architectural design decisions. Now, what we are trying to say here is that if suppose I have an architecture A. So with the help of these tactics, I'm getting an architecture A1 that would have, let's say, previously this was having a particular quality attribute A, and this time it is having a quality attribute A1, and there is a chance that this might not be having any quality attribute. So your architectural tactic moves from one architecture to another, where a parameter of the quality attribute models the move in a known direction. Right. So your architectural pattern is basically a collection of components and the interaction which we saw previously, and your architectural tactic is a transformation that will move in the direction of resolving a single quality attribute force. Right, single quality attribute force, that means we are focusing one quality at a time. Right, we are focusing one quality at a time. Now, the point is, how does one achieve quality? How does one achieve quality? Any inputs from your end? Any inputs from your end? Baseline comparisons, yes. Baseline comparison. See, comparison will be done in order to get an idea that which product fits your need, right? Or which product is better than which product. So then we do this comparison. But here, what we try to do is we apply following standard guidelines. Yes, Ramit. In this case, what we do is we add several tactics in order to achieve the quality. Right. When we are saying quality, then it means we are addressing some of the quality attributes, and these quality attributes can be, once again, your all those non-functional requirements. For example, your availability. Then we have like modifiability, if you can recall our previous discussions. We have your performance. Then we have security. So all those accessibilities will be added, testability, and then we have like your usability. So all these stuffs will be added here. Now let's see some of the tactics for to start with. Like what we have is, initially we had let's take these things. So to start with, what we have is, the first one is your availability. Now, what availability means is that I should have my system available when needed. I should have my system available when needed. And this also means we are also talking about reliability and recoverability as well. So your Bas, Clements and Kazman book gives you a definition that availability refers to the ability of a system to mask or repair faults that the cumulative service outage period does not exceed a required value over a specified period of time. So let's say, for an ATM, what we say is that the downtime of the ATM should not be more than 30 minutes over a period of 10 days. Right. So in that case, my system is available for remaining time duration. Now, if you're talking about this, so it is also related to your security, where I have like denial of service DOS attack. I have performance. That means if the response is very slow, so that is something which is to be considered. So when we talk about availability, so it's like I can detect the fault, I can recover from the faults, I can prevent the faults, uh, I can go for preparation and repair, I can go for reintroduction. So in order to detect the faults, what we can do is we have several tactics. We have like a good list of tactics starting from ping or echo or monitor, or I can have a heartbeat, I can have a timestamp, I can have any sanity checking mechanism, I can have like condition monitoring, I can go for a voting, I can go for exception detection as well, I can go for a self test as well based on what kind of tactic I am implementing. Right. So to start with, what we have is uh, the first one which I am taking is your, sorry, ping and echo. Now, this is dealing with the availability. On top of it, it is working for fault detection as well. How we'll see with the help of this particular diagram. Now, what we have is on this side, I have a system, let's say S, and this is connected to a server, let's say SE, and in between there is a connection. Right, in between there is a connection. So, in order to get the availability factor and the fault detection as well, what I can do is from this system S, I can send a ping instruction to this server SE. Further, in return, this server responds back with an echo. Now, when the system gets to know, this particular system gets to know that, okay, there is a response which I have received from a server SE. In that case, the system S gets assured that the server is working fine and it is available for me for any particular usage. Now, this ping and echo is something which you are doing on daily, almost on daily basis. Right. This ping and echo is something which you are doing on daily basis. Uh, I hope you are able to get what I'm trying to say. Yes or no? Right. Right. Yeah. Yeah. So I can see some response from your end. So this is something which we are doing on our day-to-day basis, and There's the same thing where we go to the command prompt and fire a ping query, and if my server is responding, I get an echo, or else I get a message that requested timeout. That means for within a period of or within a timestamp of t1, if I have not received any response from the system, that means my system is unhealthy, server is unhealthy. But there are some issues associated with it. Right. See, one thing is like one component in this mechanism is issuing a ping, which is like this system is issuing a ping and is expecting to receive back an echo from this system. That too within a predefined timestamp. Now the problem is, in order to get to know about the health of the server SE, let's say this, in order to send the ping, this consumes time t1. In order to receive the echo, this consumes time t2. So the total time is t1 plus t2, and within this time frame t, if suppose I need to perform something very urgent, then obviously I'm losing a good amount of time. So for that sake, I have an improved tactic, which is reducing this particular timestamp. So I'll be definitely discussing that particular tactic in next few minutes, but I want to know some solutions from your end in order to reduce this particular time frame t and make it much more effective. So I need answers from your end. So ping sends some information of content it is asking, and server sends the information record while echoing. Send requests that need to perform along with ping. No. Not the optimal solution. So what we have is although see whatever you have suggested, there is a possibility, but let me optimize it. So what I have here is I have a concept called as heartbeat. Now this will also cater to our need of availability and your fault detection as well. So what we are going to do in this, I have once again the same system. Yes, I have a server SE. Now instead of going for ping and echo kind of concept, I'm going for something which is called as heartbeat. So it's like every time server is sending a message saying, okay, so Sanyam has already given this particular solution. Server can send echo periodically. Very correct, Sanyam. So server can keep on sending this particular. See, if I'm saying server for this system, so it does not mean only server. There is a possibility when I have like two systems, S and SE, connected to each other, right? So it's not always server, but in order to explain you things that since you are very much familiar with that ping concept, so I'm using this term server. So it can be other system as well. So this other system or the server can keep on sending a heartbeat, which is nothing but an echo that says, I'm okay, I'm okay, I'm okay, I'm okay, right? So what we see is that in this case, the only time consumed is T2. I don't have to worry about T1, right? So this T1 does not even exist in this case. Looking at this particular thing, I have reduced this timestamp drastically. Right, and it's like one-way communication only. So there isn't a fear that okay, I may lose ping in between. So that means while communicating this ping, there is also a possibility that I may lose this particular ping as well. Right, in rarest of the rare occasion. So that particular part is also taken care of, and in case of heartbeat, I'm only sending. There are still issues associated with it, but comparatively, it is much more better than your ping and echo concept. You see, in this case also, you may say that my heart, the heartbeat which is sent by server can get misplaced, and we may lose this particular packet somewhere in between. So possibility exists, but as I said, not the best, but still far better than the previous system. This thing helps you in a way that one component emits a heartbeat message periodically and another will be listening to it, right? So that's how this becomes your effective way, right? Effective way of handling this thing. Now, another thing can be a theoretical part, but obviously deals with several algorithms, which is your exception detection. Right. So once again, we are only focusing on availability part and your fault detection part. So what we can do here is, in case of exception detection, when a fault occurs, in that case, an exception is raised by the faulting process itself. That means this system SE itself, declares that okay, I'm unhealthy. Right. This particular exception system SE declares that I am unhealthy. So I'm not drawing any diagram, or neither I have added any diagram in my PPT as well. I'll share the PPT as well, because what it does is the diagram remains the same. The only role of SE is to declare or pass on a message declaring that yes, I am unhealthy. Now there is another solution or another tactic available, which is very costly though, but can be implemented, and this tactic is voting. Right, as I said, once again we are dealing with your availability part and your fault detection part. Okay, wait, sir. Ramit has a question. So, sir, in this scenario, there need to be a self-assessment of the server. Yes, right. Because server itself has to respond back that okay, I'm going unhealthy. Right. See, if you see the real-time scenarios, many times these servers who are catering to various needs and lot many services are running. These servers need to be, uh, kept in a way, and tactics are added to be in a way that automatically, the moment server goes down, it declares that okay, my health is degrading, it's time to restore the services, or revamp the system, and then make bring me live. We'll see some more tactics for those things, but yes, there is a possibility for this particular thing. Now this tactic, which is voting, which I'm going to cover now. But before that, I hope, Ramit, I'm able to address your doubt. Okay. So this particular thing is voting, where what we have is, we have, let's say, several systems, right? We have several systems like your A1, A2, A3, and so on and so forth. And what we are doing is that we are running the same functionality, let's say F1 on this, same functionality F2 on this, same functionality F3 on this. And let's say these, we have several systems and the same functionality is running on it. And let's say A1 returns the result R1, A2 results the result R2, and A3 results the returns the result R1. So these things are sent to this particular system V. Now we will take a cognizance that okay, two of the systems have given the results R1 and one has given R2. So that means declare this particular thing as faulty and consider this result R1. Right. So this is like executing the same functionality in more than one component and take the majority voting. As simple as that. But looking at this particular setup for this particular tactic, this turns out to be a very costly affair. Although it is, very much popular in hardware systems. Right, this particular voting concept or the voting tactic is very much popular, but yet it's costly. So the popularity is there in case of your hardwares only. Right, for softwares, if the hardware is efficient, so software, if I have a same set of software which is running these functionalities, right, for these, for this functionality purpose only, then obviously the chances are that every software is going to give the same results until and unless there is a major change in your program, right? That kind of thing is there. And anyways, if suppose I have tested my product P, which is a software, so definitely it is meant for a functionality F1, right? And so what I'm going to do is, uh, obviously that would be a replica of it. Now in this particular figure, I have mentioned F1, F2, F3. You can take it as F1, F1, F1 only, because we are saying that we are running the same functionality, right? Or you can say that F1, F2, F3 are same things. The only thing is that we are getting results R1, sorry, we are getting the result R1 in this case, and we are getting R1 in this case. So we went for a voting. We found that okay, two systems running which are running the same functionality are getting the same result. So we'll vote for this. Siddharth. Now the question is, this V is nothing but a system which is analyzing the votes or the answers or the outcomes or the results by these three systems, and then taking a call on considering which result for this particular functionality. Okay, yeah. So any doubts, up till now? If all give different results, Sanam, yes. So we may come across a situation when all these systems are giving different results. Then we have to take a call on either looking for the functionality, which is F1, F2, F3, or else we have to take a call on looking for the working of this A1, A2, A3. So what if there is a tie? Okay, let's say here we have three systems. So in that case, if suppose I have added four systems and two are giving R1, R1, two are giving R2, R2, then obviously we have to take a call on this, because see, we have to somehow come up with the ultimate solution, and these things we may face, right? So if there is a tie, so you have to take a call based on your wisdom and your previous experience, or else simply you have to check at least two systems, right? Because two systems, each from a bucket which is giving a result R1, each another from a bucket which is giving a result R2. So can we give weights to the voting? So Ramit, obviously I can understand, if you are going for that particular calculations and all, you can definitely assign a weight to all these things. And yes, if let's say if I have more number of systems, A1, A2 up to AN, then obviously let's go for giving weights. But that particular thing is not yet required. As I said, that this is something which is popular in hardware. So obviously, if suppose I have come up with, let's say, two chips, right, two kinds of chips, right, so I'll have or maybe two three kinds of chips, so we'll deal it accordingly. So any other doubt? No? Okay, so let's move to a different quality. So previously it was fault detection, right? We were looking for availability. Now let's talk about recovering from faults. See, there are, as I said, there are a number of tactics. We are covering the important ones. So let's talk about recovering from the faults, because we have detected that there is an issue, but let's try to recover from it. So in that case also we have several options. As I said, we are talking about availability, right? So here now we are looking for tactics using which we can recover from the faults, because previously we had the tactics to detect the faults. This time we are now going to recover from the faults. So in case of recovering from the faults, we have like several things. We can prepare and repair, and we can reintroduce. In case of preparing and repairing, we have like tactics like active redundancy, passive redundancy, we have a spare, we have exception handling, we have rollback kind of concept, we have software upgrade, we can go for retrying, I can simply ignore the faulty behavior, then I can degrade or I can reconfigure systems. So we have several options available once again, right? So we are going to cover some important tactics in this. So to start with, what we have is we have something called as your active redundancy, right? So in this one, see, still we are working on availability only, right? So what we are trying to do is we are looking for availability only, just like in our previous part, but fault detection was our main focus. Right now I'm going for recovery, and I'm going for preparation and repair. So what we can do is I can run the same thing, but in case of active redundancy, I can run the same functionality on several components, and all the components will respond to events in parallel. Right, that means I have a system S, I have a system S prime, and it is running the same functionality, right? That means S, and there is a functionality, let's say F here, so there is the same functionality F on this system as well. And what is happening is all the systems are responding to the same events in parallel. That means this S is responding to, let's say, a system S, right? Or let's say this is responding to a system A here, this is also responding to a system B here. In that case, what is happening is, even if let's say S fails, right, then S prime will still be available. Right, S prime will still be available. That's why see, it is like both the functionalities running in parallel, all the components responding to events in parallel. That's why the term it is called as your active redundancy. That means both the systems are working on this, and they both the systems are on the same page. That's why, on this end also, S is responding to A, S prime is also responding to A. So if suppose S goes unhealthy, right, S goes unhealthy, let's say, in that case S prime is still active and responding to both these systems A and B. So it's like I have, let's say, uh, two VMs, two virtual machines, which are running on cloud, that too in a sandboxed environment. And both these systems, are running the same functionality, right? It can be like the same MIS, and it is responding back to all the queries to all the systems. And as I said, it's in sync. So it's like a kind of model where I have extra budget. So I'm, instead of procuring a single VM, I have procured two VMs, both the VMs running the same functionality or the same software or the same, tool, software tool, and responding back. And whichever goes down, I don't have to take care of. And the second one is always available. The only point you may say that what if both the things goes down, right? For that sake we have several improvements, right? For that sake we have several improvements that we'll cover in next tactic. Now, any doubts in this? Any doubts in this? No. Okay. So what we have is, in fact, you might have got a clear cut idea, right? Here what we had was, we had, active redundancy. So obviously my next thing will be your passive redundancy. So once again, it is catering to the same need, which is your availability, recover from faults, and prepare and repair. Right. So, in fact, I'll for active redundancy, I'll give you another example. Right. I think it was last class or last to last class when once again my system went for software update, and I requested my colleague for the system, and all the functionalities, that means all these one node and other stuffs were running. So what we did was, what for me it was easier, right? I went for teaching. Just like today also, you can see here I'm still once again sitting on this update. This update is, sorry, system is ready for another update, but what I've done is, to for the availability sake of availability, I haven't started any possible update in this particular system today. Right, so that kind of thing we have in case of active redundancy, where I have the availability. I know I have another system, so I can make it easily available. Now, next is your passive redundancy. So what we do is, once again, I have, let's say two systems, B and I have another B prime, and it is responding to a system, let's say A here, and it is responding to another system P here, and in between what I have is, I have a sync mechanism. Right, in between I have a sync. So one component, the primary one, responds to the events and informs the other component, which is the secondary one, of the state updates it must make periodically. Right. So in fact, this tactic, you can say it emerged from that same concept of a database management system. So what is happening, this system P is running, let's say, some functionality F, which is now, you know and what it is doing is that, after regular intervals, a sync process is taking place. So this F is also available here as well. And what happens is that, in case this system B goes down, so I know that this B prime is in sync, so it would be catering to the needs of this A and B. Right, this would be catering to the needs of this A and B. This is somewhat similar to, you can see here also your screen is there. You can see this sync is going on, right? Page sync status. So it's like it is continuously syncing to, Microsoft's cloud, and there is another replica made available. So let's say, if suppose I lose this tablet, I still have this replica, and uh, from a different system, if suppose I log in, and then once again the same part will be available. So here also what it is doing is, if suppose, because I gave you an example where I'm losing a system, but here also, it suppose, even if suppose the system goes down, this is also an example of, losing a system in a different way. That means it's no more available for responding back to my queries. So in that case, I go ahead with passive redundancy. Now, any doubts in this? Any doubts in this? I hope you people are here only because I don't see any response from your end. Yeah, okay. Fine. So next thing is a spare, but before addressing, I thought some of you will raise this particular point. Uh, so the next part is I have a concept called as spare. So once again, we are working on your availability part only, and we are trying to recover from faults. So that means your preparation and repair. Now, one thing is, let's say sync process was about to start, and in between this went unhealthy. In that case, I lost some information. Losing an information is still okay, right? I can move back to the previous first stage. It's like you went for an online transaction and your payment failed. So payment failed is okay as far as you're able to get uh, your amount back. But if suppose there is an issue that okay, somewhere you lost the track, and then in normal conditions, what happens is you get in touch with the payment gateway people, you write an email, you share the screenshots of, and then transaction ID and the failure and anything else. So then what is happening is in this case I have, or maybe the literature has brought a minor change. Right? Literature has introduced a concept of a spare system. Right. So same setup, and same setup. Okay, here I made a mistake. It should not be it. Let me add C. So what is happening is in between I have one. See, these small circles are connectors and not more than that. I have P, which is nothing but a persistent system. See, all these things are happening because I have a good budget. Persistent component or persistence system. So what I'm doing is I'm adding a standby component which is configured to replace the failed component. That means if B goes down, I know my B prime is ready. But when B goes down, this persistent system or the component is going to ensure that this spare, which is B prime, so this spare, which is nothing but my B prime, is sufficiently fresh before resuming the services. Right. So it's like your Amazon, you're making a transaction on Amazon, and then all of a sudden payment fails for, let's say, some reasons due to internet connectivity or so. Then I know I'll have a fresh start. I'll not be somewhere in between where OTP has to be generated or OTP is generated and transaction is to be completed. So it will be like a fresh start where Amazon gives you a scope of making a repayment for this. So that kind of setup we have here. This kind of setup is only possible when I have good amount of budget. Right. When I have my higher budget, then only we are going to go for this kind of setup. Now, any doubts in this? Okay, Siddharth, yeah. So can you explain this again? Yeah, definitely. So this passive redundancy and active redundancy, everyone has the idea now. So there was a problem that a transaction started which was not yet synced with B prime, and B went down, B became unhealthy. In that case, I'm observing a failure for a particular transaction. So to improve this particular thing or to get rid of this particular problem, what I'm doing is I'm introducing a persistent system in between, and I have this standby component which can replace this failed component, right, which has gone down, which is unhealthy now, with the help of this persistence component, which ensures that the spare is, which is this one, spare is sufficiently fresh before resuming the services. So it is not encountering that kind of issue where the sync was not over and the system went down. Right, where the sync was not over and the system went down. So that kind of thing is not observed here. It's a role of persistence component to deal with these kind of situations where I know that the sync is done up to a certain level. Right. This is somewhat similar to, there is the next tactic which you'll see will be similar to what you see in case of, in your database management system, you saw the concept of commit and rollback. Right, rollback we'll once again, be covering in next tactic. I think the next tactic is rollback only. Right, in your database management system, you know, there were several labels, or you can say checkpoints, right, where you were going for committing, and then your rollback becomes easy to the previous committed position. I hope you can connect from this particular discussion. Or maybe let's cover rollback, then the things will be much more clearer. So what we do is we maintain a log file. So what we're going to do is, now we're going to talk about this rollback, right, which is nothing but a tactic for availability, where once again we are working on recovery from fault and preparation and repair. So what we do is we create a checkpoint, and when the system fails, the state gets inconsistent. So what we do is we restore the system using a previous checkpoint of a consistent state and a log of transaction. So what we have is, let's say I have this. So every time a log is maintained, and I'm creating the checkpoints as well. So in that case, whenever my system is whenever my system fails, I'll get, or I'll move back to the previous consistent state with the help of this log which I'm maintaining. This log can be maintained on a regular interval. right? And then I can bring back the services. Any doubts in this? How would the spare component know when to replace no, there isn't any spare component in this, Tanveen. Your point is logical, but the thing is, I don't have a spare. I'm only maintaining a log. So, okay, in the previous tactic, right? In the previous tactic. So, now the role of this persistent system is to give you a fresh start. So, fresh start will be, that means I'm getting a message from here, and then this becomes active and this becomes inactive. Right, this part becomes inactive, this part becomes active. So that's why we have introduced this particular persistent system. Clear? Yeah, okay. So in this one, it's like I have to wait for, if this system goes down, I have to wait for this system becoming available once again, and by help, with the help of these log files. Now there is another tactic, you know, which is your shadow operation. Once again, for I have this for availability, where I have recovering from the faults, and then reintroducing. So here what I'm trying to do is I'm going to run a previously failed component that too in shadow mode. Shadow mode for a while, to make sure it is working properly, and then resuming its services. Right, so no diagram for this. What we are trying to do is, I am running a previously failed component in a shadow mode, and I'll make sure that it is working fine before resuming its services. Right, so your last tactic in this part will be the state race synchronization. So this is nothing but the part of passive redundancy. So when the component needs to be synchronized, and what we do is that, let me move back to the passive redundancy. Sorry. So what we do is, so the part of passive redundancy, when the components need to be synchronized, and in what sizes the issue dealt with in this particular tactic. So what we do is, we go ahead with state resynchronization. Right, so I need to take a call on the state in this particular part. That's the only difference and rest everything remains the same for state resynchronization. So in our next class, we'll talk about fault prevention, right? Or maybe we can have a discussion on fault prevention as well, because that's also part of your availability only. Still we are dealing with availability. So here what we can do is I can have system removed from the services. I can look for transactions. I can look for predictive models. I can look for exception prevention. I can increase the competence set. So I'll address at least one tactic, right, which is your transactions. So as I said, it is dealing with availability only, where it is dealing with fault prevention. So what we are trying to do is, let's say I have this system A, I have here C, and here I have transactions. Right. So what we do is we bundle several sequential steps such that the bundle can be undone together. Right. So we are doing the bundling of the operation, the transactions. So this will prevent any data to be affected if a component fails. That means we are following a very popular strategy of all or none. That means if a transaction has started, so this will end, or that means the transaction will be completed, or else the entire transaction will be removed. So it will be a bundled package. Right. So that means if payment initiated, that means a debit took place, so it will credit to some place, or else nothing will take place. Right. Or else nothing will take place. So this was all from my side for today's discussion. Let's take some questions now on the topics which we have covered today. Let's take some questions now.